6-5. I'm gonna show operations with expressions how to add without subtract. Oh man, what a nice intro for you guys. Here in 6-5, you're going to be simplifying some radical expressions. You're going to need to add, subtract, multiply, and divide radical expressions also. So unfortunately in 6-5, these are not as nice and pretty as the numbers in 6-4, although it still helps to know your perfect squares, cubes, fourths, and stuff like that. So if we want to simplify radicals, the properties you have to use are also, like we used in 6-4, are going to be the same that we used in 6-5. So let's go through something here. Whenever we try to simplify a radical, whether it is whether it's a number or a variable underneath your radical, it doesn't matter if it's a square, a cube, a fourth, or a fifth, then you just have to keep in mind that in order for a radical to be in simplest form, the radicand must contain no factors that are nth powers of an integer or polynomial. So that means that if we have, let's see, oops, sorry, just write no here, no factors. So that means if you have a square, then you're gonna, in order to simplify it, you have to get a perfect square out. If you have a cube, any perfect cubes can be factored out as well. And so this holds true for, like I said, squares, cubes, fourths, fifths. And what we're going to do is we're just going to make sure that we don't have any factors that are of integers or polynomials in here. So when trying to simplify a root, you have to remember all your perfects. So perfect squares, obviously you have 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25. You should know all of these up through 20 times 20. So then you go 36, 49, 64, 9 times 9 is 81, then you have 100, 11 times 11 is 121, 12 times 12 is 144, 13 times 13 is 169, and then we get to the harder ones. 14 times 14 is 196, 15 times 15 is 225, then you're going to have 16 times 16, which is 256, 17 times 17, which is 289, 18 times 18, which is 324, almost forgot it, 19 times 19, which is 361, and 20 times 20, which is 400. Those are going to be the most common perfect squares you're going to see that could be factors of a number underneath a radical. Now perfect cubes, you really should only know, you only have to really know these from like, 1 to the third up through 10 to the third. So if you know 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is going to be a 64, 5 to the third is 125, 6 to the third, what's that, 216, 7 to the third is 343, 8 to the third, that one's a little bit tougher, so if you have 8 to the third, that means you're going to have a 512. Don't really run into that as much. 9 to the third is 729. You will probably run into 10 to the third, which is 10,000. Perfect fourths, if you know these through 5, you should be good. So 1 to the fourth is 4, 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth is 256, and 5 to the fourth is 625. And perfect fifths, really you need to know 1 to the fifth is 1, 2 to the fifth is 32, and really if you know 3 to the fifth is going to give you a 243. Usually those ones you need to know. If you have a 4 to the fifth, that's going to be 1024. 5 to the fifth, which you rarely ever run into, is a 3125, but I think you might have to do the 1024 on one of the problems. So let's move on to our first example here. And if we want to simplify this expression, what we're going to do is we're going to simplify each product or each of these terms individually. So you're going to simplify the 16 separately from the P and from the Q. So I'm going to write them out as individual factors. So we're going to say square root of 16 times square root of p to the 8th times square root of q to the 7th. So if we simplify these, we know the square root of 16 is 4. And for polynomial or for variables, you take the 8 divided by the index, which is a 2. So 8 divided by 2, there's a little 2 there. We just don't write it, is p to the 4th. Now we run into an issue because 7 divided by 2 is not a pretty number. Instead, 7 divided by 2, well, 2 goes in there 3 times, minus 6, gives you a remainder of 1. So what this 3 and what this 1 represent are your exponents that are left over. So you're going to have a q to the 3rd on the outside, and then you're going to have a remainder, which is a r, underneath of a 1. So here's your 3 remainder. I think a radical 1 is underneath. So in your final answer, what you have to do is you just combine everything that's on the outside, usually put in alphabetical order, so 4p to the 4th, q to the 3rd, and then leave whatever's not outside your radical underneath. So in your final solution is a 4p to the 4th, q to the 3rd times radical q. Same thing is going to be done on b. We're going to separate these, simplify them separately. So we're going to say the square root of 1 over 25 times the square root of a to the 4th times the square root of b to the 9th. So if you take the square root of 1 over 25, that's a 1/5. Oof, man, my pen is just not working very well, sorry. That's a 1/5 times a squared. Now b to the 9th, remember we're going to take 9 divided by your index, which is a 2, gives you a 4 with a remainder of 1. So these are your numbers that are going to go on the outside. Remainder 1, that's going to be your b underneath. So you're going to have a b to the 4th on the outside, and then you're going to have a radical b to the 1st underneath. So very similar. So your final answer ends up being a 1/5 a squared b to the 4th radical b. Whatever's underneath cannot be a larger exponent than your index. Okay, so since you have a 1 here, that has to be less than a 2. If this is a 3 on the outside, then this could either be a 1 or a 2. If this is a 4th root on the outside, then this could be a 1, 2, or 3, but it cannot be a 4 or larger. So here is your solution. Now when we get to part C here, what some people forget is if you have an odd index, you can actually have a negative underneath your radical. If you have a negative underneath your radical and you have an even index like a 2, a 4, or 6, which we probably never see a 6, but a 2 or 4, then you can't have that and you have to bring it out as an I. But this can be rewritten as the cube root of -1 times the cube root of, well, we need a perfect cube that goes into 5,000. So if we look at our list of cubes, largest one we have, oh hey, there's 1,000. So what we'll do is we'll split this up into making this a 1,000 times the 3rd root of 5. These are thirds out here. So if these are third roots, cube roots, you have to write the 3's. So the 3rd root of -1 is -1. Times the 3rd root of 1,000 is 10. Times the 3rd root of 5, well, that can't be simplified any further. So your answer ends up being a -10 times the, not the square root, you must write that 3. If you don't put that 3 in your answer, then it's going to be assumed that it will be a square root and your answer will be incorrect. All because you forgot this little tiny 3. Oh, aren't you so cute, little tiny 3? Alright, last one for example 1. Simplify the 48, the v and the z. So let's split this up. Now we're doing 4th roots. So we're going to need to keep our 4th roots handy here. And we're going to have to simplify by finding a perfect 4th that goes into 48. So z to the 13th. So a perfect 4th root that goes into 48. Look about your list. 1, 16, 81. Okay, well, obviously 81, 256, 625. Those are too big. 16, is that going to 48 evenly? Oh, hey, yeah, it does. So this will be 4th root of 16. That goes in there 3 times the 4th root of v to the 8th, which we're going to be able to simplify. And actually, you can simplify that to make that a v to the 2nd, because you're taking 8 divided by 4. Times, now this one's a little bit trickier, because we're going to be taking z to the 13th divided by 2. Well, that goes in there, actually not by 2, we're going to divide it by 4. So 4 goes in there 3 times with a remainder of 1. So that's good, we get a remainder that is smaller than our index. So we have a 3 and a 1. So when we write this, this will be a z to the 3rd times the 4th root of z to the 1st. So then this 4th root of 16, remember that simplifies and that can become just a 2. So we have a 2, a v squared, a z to the 3rd all on the outside. 2 v squared z to the 3rd, and then underneath our 4th root, don't forget your 4, you have a 3 and a z. So that is how you simplify a square root, a cube root, and a 4th root. You have to look for factors that are fourths, cubes, or squares.